Thank you for all for coming here. I'm not here on behalf of the Lego company. I'm a hobby builder, really. I'm not a real engineer myself. Oh, no sound, please. So please don't mind if I use too many layman's terms. And it's all going to be about mechanics done with toys. Hopefully. It's okay the way it is. No, I don't. No. All right, so
Very sorry for that.
yeah, sorry for that. And after this great beginning, this is a short video of my custom models. What I do is actually, basically, I design and create my own custom models, which are not Lego sets. You can buy them. These are one-off builds, all designed from scratch. Yeah, and we have a lot of fun with them. And I also cover some sports events that Lego fans do. I also travel to various Lego exhibitions. You can see all of this stuff at my video channel, which I will mention later. And I also review the official Technic Lego sets. I get them directly from the Lego company. And every Lego Technic sets in the last few years has been reviewed by me, including this one, which you may be familiar with. Yeah, these are my hands. I'm hiding them so you can't really compare, but yeah, that's me. Yeah, to let you know, I have my little assistants, hamsters, because I've made a mistake once of showing a hamster with Lego to YouTube audience, and they are not letting it go ever. I'm forced to use hamsters now repeatedly. As you can see, they make great cheap models. The salary is not too high. Mostly food, yeah. All right. You know, we have our disagreements about that. The presentation? Oh, Cool, great, thank you very much. So this is typically what, unfortunately, building with Lego looks like in everyday life. It looks childish to most people. It looks suspicious to the Lego company itself, I'm pretty sure. And the last picture, it's ordering new pieces from a website that sells them. And there are periods of time when I do more of that than I actually build with these pieces. So that's the sad reality. And now I'm going to try to make it look nicer. Essentially, we're going to talk about how we go from this to that. This is one of my custom models. And I divided this talk into 3 parts. The first part is about the Lego pieces these days, the potential we are dealing with, the kind of stuff you can get from Lego sets nowadays, because the potential is enormous, and it's much more than just these simple building blocks you can see here. The second part is about real-life mechanisms that you can recreate with Lego pieces. And the third part is going to be about some of my models, the process of how such a model is created. And you are going to see sort of a backstage view of how this all happens. So I'm going to start with the essential part in making your models work and move, the gear wheels, of course. And these are all the types of gear wheels used by Lego today. There are older systems of gear wheels that are not presented here because they are long gone of use. The numbers of the top are the numbers of teeth. We use them to calculate gear ratios between the gears. And as you can see, there are 4 basic types of gears. There are spur gears with square teeth, which only mesh at parallel with each other. There are bevel gears with chamfered teeth, which can mesh at parallel, but also at right angle. Then we have a knob gear, which is a very unique Lego piece because it can mesh at parallel and at right angle, but only with another knob gear. It's impossible to mesh it with anything else, so it always creates 1-to-1 gear ratio. And finally, we have a worm gear, which is a very special piece that you can often see in the real world. The worm gear is special because it can only drive other gear wheels, but it can't be driven, or it can't drive another worm gear. Let me give you a real-life example. Let's say you have a railroad crossing and barriers that go up and down. You need something to make them go up and stay that way. And this is perfect application for the worm gear, because when it drives a gear that's sitting on the axle together with the barrier, if it drives it up and it stops, the barrier is going to stay that way, because the gear wheel on the axle with the barrier can't drive the worm gear. There's too much friction. In the real world, there are some special worm gears that can be driven, but it always involves a lot of grease, and we don't use grease in Lego. That's one of the limitations we are working with, officially at least. Yeah. Continuing with gears, this is something you may be also familiar with. It's a differential gear. It comes in 3 types with Lego. It's an identical piece you can find in your own car. It drives the rear axle usually. It's used to, as the name implies, differentiate speeds between the right and left wheels, so your car can make turns without drifting. And I think the interesting thing from Lego is that one of these variants, as you can see, the one on the lower right, it can be locked. It's designed to be lockable, just like in real off-road cars like Land Rovers and Jeeps, where if you want to handle some serious off-road obstacles, you need to lock your differentials so the wheels don't slip. You don't do much turning then, but you can handle some serious obstacles. And I think it's pretty impressive that Lego has actually designed some part. We didn't have to, come up with some way of doing it ourselves, but it's done by design. Another great example of limitations that are inevitable when building with toys are turntables. These are turntable gears. A typical application for such a piece is making some large structure rotate around itself. For example, a mobile crane and a support structure in it. You want it to rotate left and right, this is the piece you need. And the trick is that in Lego there are no bearings, no ball bearings, no roller bearings, no bearings of any kind. What you have here are just 2 plastic pieces inserted into one another, and as you can imagine, the friction between them is immense. We are losing a lot of effort from the motors, from the hands, if we are using hands, just to the friction alone. So this is something we have to work with. Of course, there are ball-shaped Lego pieces, so you can sort of try to create your own custom ball bearings, but they are not very effective. They are always inevitably pretty huge, and they tend not to stay together as well as you would like them to. I'm talking from a sad experience. This is really cool part because this is part used to create transmissions. It's easy to make transmissions. As you can probably know, the transmissions come in 2 basic types, synchronized and non-synchronized. If you have ever driven an old bus or a very old truck, you might have dealt with non-synchronized transmission. It's easy to recognize because the gears tend to grind when you shift or lock up completely. And it's easy to make such a transmission with Lego pieces. But we don't want any grinding here, so the red circular piece is called transmission driving ring, and it's created by Lego specifically to allow synchronized shifting. So it allows shifting speeds in a transmission at any speed without stopping whenever we want. How it works. If you look at these 2 dark gray gear wheels on the sides, they have round holes in them, so they can rotate freely on the axle that goes through the entire stuff there. In order to make them stay rotating together with the axle, they would need cross-shaped holes. And they have round shapes, so they can rotate freely. However, the red ring, it does rotate together with the axle. And now, if you slide it into one gear or another, it locks that gear with the axle, so the gear starts rotating at the same speed the axle does. And it's a pretty simple solution, but it allows us to do a very crucial thing. It's done, by the way, using this piece on top. It's called catch. It can put the ring in one of the 3 positions, far left, central, or far right. The central would correspond to a neutral gear in a car. And this is a practical application of such a piece. What you can see here is a very simple transmission that sits between a motor and the wheel. So it's the same situation as in a real car where the transmission is between the engine and the drive and axle of your car. it allows us to choose two speeds. What you can see here are two sets of gears on the left and on the right. And the gears on the right, as you can see, there are three identical ones. They are the same in size. So meshing them, driving them with the driving ring, it doesn't change the gear ratio, meaning that the axle and the wheel, it rotates at the same speed with the same torque that the motor does. However, interesting thing happens if we mesh the left set of rings as shown in the middle. Just a second. Because as you can see, the first upper two gears are identical, but the other two gears on the lower there are not. First gear is 3 times smaller than the other, and we know that by simply counting teeth. The first gear wheel has 8 teeth, the other has 24, so it's 8 to 24, 1 to 3. And by driving them this way, we create 3 to 1 gear ratio between the motor and the wheel, meaning that 3 rotations of the motor translate into just 1 rotation of the wheel, but at the advantage of increased torque, meaning that the motor only needs to exert 1/3 of the force it would otherwise need. Meaning, again, that if you have a motor that is capable of driving only vehicle weighing 1 kilogram, with this gear ratio, it can drive a vehicle that weighs 3 times as much. So that's the basic idea of the gear ratio. This is entirely another nice thing from Lego. It may look a little weird. It's a pneumatic system. It's based on the real-world hydraulic systems, which you can see commonly, for example, in excavators. A typical excavator, as you know, has this big digging arm that has several sections that go up and down. And what moves these pieces are cylinders that extend and retract. In Lego version, this is done using compressed air in this system. In real life, it's done using hydraulic fluid. But of course, Lego is designed to be safe for kids, and again, there are limitations. We don't want them to play with any fluids, especially not before 21. So the first part, the part number 1, it's a pump that pumps air into hoses, connecting it with other parts. It can be operated by either hand or by a motor, which creates an electrically driven compressor. The part in the middle is a valve. It has a lever that decides, setting the lever dictates which way the air is flowing. The lever, just like the driving ring, it has 3 positions: far left, central, and far right. Setting it to central cuts off the flow of air completely. And the third part is a pneumatic cylinder. This comes in many variants in Lego, and it has a very simple job. It extends or retracts depending on which way the air is flowing. So yeah, we are going to hopefully see some examples of that, but now I'd like to move to the second part, which is some real-life mechanisms recreated in Lego, because what I find fascinating about Lego is even with all these fancy, highly specialized pieces, you still can use just some basic beams and bricks to recreate mechanical solutions from real life. And I'm going to start with linkages. This is called Chebyshev linkage. And the idea here is that if you rotate the gray beam as the blue arrows show, left or right, the red pin is always going to move in a straight line, left or right. So what this linkage does, it changes rotary motion into linear motion. The yellow beam is going to tilt left or right, of course, to make up for the changes in positions of the gray beams. However, the red pin, because it's in the center, perfectly in the center, is going to stay level as it moves left and right. The same thing is done by this mechanism, whose name I'm not even going to try to pronounce, sorry. Here the idea is that you have this yellow beam, which you can rotate left or right, and again, it's going to make this red pin move up or down in a perfectly straight line, because the dark blue beams are going to even out the differences in circular motion here. It's best shown in motion, but I'm sure that we have many engineers here, and it's probably a piece of cake for them. Another example of the same mechanism that does the same thing is the Watts linkage. Here, it's really just a different variant of the Chebyshev linkage if you look really close, because you have, again, 2 beams that you can move, one or the other, the dark blue ones. We have the light blue beam that will tilt as we move this. However, the center of it, with the red pin inside it, is going to, again, move in a perfectly straight line up and down. And now this is a really fun mechanism. If any of you have studied history, it has some very interesting applications despite its apparent simplicity. Because the trick here is that we have these two pins, red and green. And when you move one of them any way you want, the other is going to copy its movements, but with a larger scale of movements. It's going to perform the same movements, but further, in case of the green pin. So imagine, for example, a historical application for this mechanism is that you can have two pens, red pen and green pen. And let's say you are drawing a map with the red pen. So what the green pen is going to do, if you put a sheet of paper, of course, somewhere near, is it's going to draw the same exact map, copy the same exact movements you are making with the red one, but at a larger scale. So this is a nice way to redraw your maps or other stuff into smaller or larger scale. And you can actually adjust the scale this is happening at, because it depends on the difference in lengths of these two horizontal beams. As you can see, the lower one has 5 dots. It's 5 dots in length. And the upper one is 11 dots long. So the difference between them is going to be just slightly above 2 to 1. You can get a twice enlarged map by drawing it with the red pen. That is a linkage used to, well, lift. It's used, for example, in some short-range elevators when you have only one floor or cargo elevators. Here the idea is that if you rotate any of the dark blue beams, or ideally both of them because of how the stress propagates in the structure, the light gray platform is going to go straight up or straight down, depending on which way you are rotating them. And this is easier to understand from a simpler version of it, which is scissor linkage. This one can be found, for example, in scissor lifts, which are commonly used when you, let's say, you want to hang a billboard somewhere high on the street. A scissor lift is what you would use. So the idea here is that you move on the bottom, you move the dark gray, the light gray pin horizontally left or right, and that makes the platform on the top go up or down, again in a perfectly straight line. So this mechanism, it translates horizontal motion into vertical motion, and the great thing about this, as you can see on the right, is that it has a really great reach. The difference between this mechanism when fully extended and fully retracted is factor of several times. You can reach really, really far with that. That one is named Fanon. It looks complex, but actually you can see that it has just a few parts. There is a round part there with a red pin in it. And if you rotate it left or right, what is going to happen is that red pin, which for some reason is gray on the other picture, but never mind, it's going to move in that gap braced by the green pieces. And as it moves, it's going to move this entire structure connected to the green pieces left or right. And a very simple solution, it's actually a very old mechanism. I believe it's medieval at least. A very simple solution would be a simple lock in the door where when you turn this circular piece and it makes these rods slide into the door or out to the door, locking and unlocking them. That one is my favorite, actually, because, of course, it was invented by German. It's going to be a little hard to see, but imagine that you are turning the green axle, and because of these all pieces in the middle, they are connected, the red axle is going to rotate in the same direction at the same speed. And now, if you pay attention to the parts in the middle, there are 3 parts. We call them rotators, blue, red, and green one. And as you can see, the green and blue one are fixed to the axles, but the one in the middle, the red one, it's not fixed to anything except the yellow beams that connect it to the other rotors. In other ways, in other way of saying, it does not have a fixed point of support, meaning that this coupling, it actually allows you to transfer motion from the green axle to the red axle. When they stay in motion, they can move relatively to each other, go closer, higher, farther apart, and the red rotor is going to move evening out this difference in positions. And the trick is that you can actually have multiple red rotors, multiple middle rotors, all of them hanging in midair, and they will all move and transfer this motion as no matter where the other two rotors are, the edge rotors, let's call them. it's best seen in motion. You can actually see one on my YouTube channel. It's quite mesmerizing to watch. Now, if anyone here has a mechanical watch, and I'm sure many of you gentlemen do, you have at least one of these inside them. The story goes that it was invented by Swiss watchmakers to make the clock hands move in an intermittent motion. They didn't want them, for some reason, to just go crazy, like that. They wanted to move by second, by second, by second, and so on. So what happens here is that as we rotate the red axle and the blue beam with it, there is a black pin at the end of it, which is going to catch into that structure on the green axle. And it's going to catch exactly once per rotation. And the structure on the green axle is shaped so that every time it catches, it's going to rotate it by only 90 degrees exactly. No more, no less. So this way we can change continuous rotary motion into intermittent rotary motion, 19 degrees, 19 degrees, 19 degrees. And then we can add some gearing that changes it into smaller pieces of the full 360 degrees. So we can have a second hand, a minute hand, an hour hand on our watch. This is even more complex. But these are simple pulley systems. If you have any sailors here in the room, they are going probably to be familiar with those. The job of the pulley systems is to save you effort in lifting loads, basically. Let's imagine that I have an imaginary piece of string with a load attached to it. Let's say it's 10 kilograms, because obviously I'm not a heavy lifter. And my job is to lift the load by 1 meter up. What I'm going to need to do is to pull 1 meter of string, exerting effort that is required to lift 10 kilograms. Now, with the first pulley system, which is called gun tackle, that effort can be cut by half. How this happens? If you pull the string up there on this reel on top, it's not going to directly pull the lower pulley, which has load hanging on it, but instead it's going to start reeling in the rope, and the pulley on the bottom, it moves at only half the speed you are reeling the string at. And thanks to that, the effort you are exerting while pulling the string is multiplied by 2. We call it mechanical advantage of 2. The gun tackle grants you mechanical advantage of 2, meaning that in order to do the job I've mentioned, which is lifting 10 kilograms of load 1 meter up, I'm going to have to reel in 2 meters of string, but only using force sufficient to lift 5 kilograms, not 10. It's cut by half. And it's usually practical to do this kind of trade. You have to work for a longer time, but using less force. It's usually practical to us because as human beings, it's easier for us to work longer, but not getting tired so much. So that makes practical sense. And it was invented in sailing when they had to set up sails, which were in history they were heavier and bigger, and this was inevitable to just create bigger ships, bigger sail ships. And the trick with this pulley system is that you can really do this indefinitely. You can increase the mechanical advantage indefinitely. Every time you add a pulley and you wrap the string again around another pulley, the mechanical advantage is going to increase. So we have a laugh tackle, which has 3 pulleys and 1.5 loop of string, and it creates mechanical advantage of 3. So again, I have to reel in 3 times as much string, but only using 1/3 of the force I would normally have to use to lift that load. In real life, there are pulley systems that go as far as mechanical advantage of 6. This is 3/4 purchase. I've seen some people go with as far as 10, but the problem with this system is that it quickly becomes less efficient at higher mechanical advantages because you have 10 or more pulleys, and all of them have the same single section of string wrapped around them, which is prone to stretching, so we are losing a lot of effectivity. And to help with that, when you need a really high mechanical advantage, we have very interesting systems, 2 of which I would like to talk to you about. Yeah, that's called power pulley system, and the trick is, if you look here, it's actually a gun tackle that has another gun tackle attached to it, another and another. The part with the black string there is just a simple gun tackle that gives you a mechanical advantage of 2. It's no different than the example we've seen here, except that the string is attached to somewhere else. But it works the same way. So we have a gun tackle, mechanical advantage of 2, again, another gun tackle, mechanical advantage of 2, again and again. And the trick with the pulley system is that these mechanical advantages, they don't add, they multiply. So you have the first gun tackle with a mechanical advantage of 2, then you multiply it by 2 again, you get mechanical advantage of 4 by 2 again, 8 by 2 again, 16. The last pulley has a mechanical advantage equal to 16, so it's pretty huge, and as you can see, we have only used 5 pulleys. Plus, we are using 4 different sections of string, so stretching does not become such a big issue because each string can only stretch a little. It's not a single piece of string in the entire mechanism. So this is much more efficient, even if it's much more complex or complex looking. And that one is actually, I believe, unique. And the story is it was invented in ancient China, which is why it's commonly called Chinese windlass. It's actually, it looks that simple, but the way it works is ingenious and quite complex because, as you can see, we have one pulley with one piece of string, which is connected to 2 drums on top. These are, in this case, we have drums, not pulleys, because we need to have some amount of string on them. So these drums, they have a different diameter, and the yellow piece is there only to separate them, because we don't want the string dropping from the bigger drum to the smaller one. That would be bad for us. And now consider what happens if I rotate the light gray axle clockwise. What is going to happen is that the red drum is going to start winding up the string, and at the same time, because these 2 drums are coaxial, they are sitting on the same axle, they can only rotate in the same direction at the same speed. So as the red drum winds the string up, the green drum is going to wind it off, but at a different speed because they have different radiuses. So because the red drum is bigger, the string is going to be pulled up faster than it's coming off down the green drum. And so the lower pulley is going to start ascending, not descending, ascending, and it's going to, the speed and the mechanical advantage we get here, it actually depends on the difference between radiuses of the 2 drums. You can see the formula here. The big R is radius of the bigger drum, the small r is radius of the smaller drum. We know that these 2 are, the red is twice the size of the green, so here the mechanical advantage is just 4. But you can increase that advantage significantly if they are very close to each other in size, almost identical. It's possible to get a mechanical advantage in this system that is like 30, 40, 50 times what you are putting into this system. Of course, the pulley is going to move very slowly with such a high mechanical advantage, but you are going to have to exert very little force with very huge loads. And there's another very cool feature of this system because, again, as you can see, the string is connected to the drums from opposite directions, despite the fact that they are coaxial. So when the load pulls on the string, it can't really pull it down. I mean, you can let go of the axle on top, and the load is going to stay in midair where you left it, because the string is pulling from 2 opposite directions on the drums. So the axle, unless axle breaks, the axle can't start spinning in 2 opposite directions at the same time. So it's a very cool feature. It not only saves you effort in lifting loads, but it's also safe. I hope that was a little clear, at least a bit clear, because now we are moving to the third part, which is advanced Lego models and how they are made. Finally, the boring part is over. Yeah. So that's one of my models, and I would like to quickly, I don't know how we are looking with time, but I would like to quickly walk you through how such a model is built. So this is one of mine. I usually build, it doesn't have actually the great proportion. It's a little too flat, but well, you can be perfect every time. The first step is when you are building a real-life vehicle or other object, is that you are looking for blueprints, which I'm sure many of you are familiar with. Basically, a blueprint is a view of an object from several angles without central perspective. And ideally, all the views should be at the same scale. And why do we need that? This is the tricky part. because we are using that to scale our Lego model to know what the dimensions need to be to maintain the proportions of the real object. Normally, I'm sure many of you gentlemen have built models in your childhood. They come at different scales, like 1 to 100, for example. And with such a model, it's easy to calculate the scale because you simply take dimensions of the real thing and divide it by the scale. So let's say, for example, there is a 100 meters long ship, and I have a 1 to 100 scale model of it. It's going to be 1 meter long. That's very simple. However, in Lego, the Lego pieces come at fixed sizes. We can't really, scale them up and down. Yes? Sorry. All right. Apologies. I hope the gentleman in the back have heard something, not just the pictures. All right. So when building with Lego pieces, you are bound to use the pieces that are fixed in size. They can't get bigger or smaller. So we have it's another difficulty we have to overcome. And what you are actually doing usually is that you start with a wheel you want to use, because Lego wheels, there are not many of them. They come in limited sizes, they come in limited shapes, and you start by picking the one that you think you want to use, that matches the look of your model, that has the reasonable size, and you scale the entire model accordingly to the wheel. This is usually done by simply printing the blueprint out, measuring the wheel, comparing it to the size of the Lego wheel, and you go from there. You calculate the width of the distance, between the front and rear wheels, the height of the body above the wheels, how far the body protrudes in front of the front wheels, and so on and so on. What you see at the bottom is a web address of a little tool I've made. It helps with scaling Lego models and other models as well, because you can load a blueprint into it. Okay, I'm sorry. I hope you are hearing me now. So as I was saying, there is a little tool I've made which helps with that. You can load a blueprint into it directly, and then if you set the point of reference for it, so it knows how many pixels are how many Lego pieces, it's going to give you measurements as you draw on the blueprints. And we get to how such a model is built. This is a very early version. It's just a base of the chassis with two stringers, I believe it's called. Two stringers that hold it together. We have a front axle and rear axle, which is not yet complete, but the front axle is complete. You can see that it has a double wishbone suspension, like in a typical real-world high-performance car. With shock absorbers, it does have steering links that allow to steer wheels left or right, even as the suspension works. And there is also a differential in the middle, which means that it's got a front-wheel drive. It's actually the model, it was Audi, so of course it had a all-wheel drive, because it's not allowed to make Audis with only rear or only front-wheel drive. I'm pretty sure I would be sued for that. Here we have a rear axle now. It's got the transmission attached to it. You can see that there are 4 motors total, 2 on one side, 2 on the other side, and 2 motors are driving the transmission because one motor was not strong enough to drive this vehicle. Again, Lego limitations. And there are 2 other motors used to operate transmission. It had 2 speeds, it had 4 speeds. So each of these 2 motors was operating 2 speeds. We also have a V10 piston engine, which is Lego ready-made. It's nothing fancy, but it looks pretty cool because the pistons can move. And we have, it's all connected to the rear axle. There is a suspension, and now we have a complete chassis. And we are starting to build the body personally. I usually start with edges of the body. So we have a lower edge on the sides here. We have a roof, so I know how far it's going to go, how much room I have under it. We have a hood again, so I know how much I can fit in front there. We have base for the front grille, which is very beautiful in Audi R8. And there is a beginning of the support structure for headlights and such stuff. And headlights are here. This is where I was experimenting with how to recreate the beautiful headlights of the Audi R8 with Lego pieces. It's actually what you are seeing here are only two LEDs, only two. All of the other stuff that lights up is illumination from these two LEDs because there are chromed pieces used around it to increase the illumination. So it's you are using very little lights to create a very nice effect with a lot of illumination. And this is almost a complete model. The rear end is not yet complete, but as you can see, it has the front end, the middle are complete. There are custom stickers on it, and this is a complete model. It had all-wheel drive suspension, 4-speed transmission, V10 engine. It had a lot of stuff that the real car does, except it wasn't exactly as cool or as sturdy, because it was all made of little plastic bricks, and there's a ton of limitations with that. I can tell you, for example, that performance-wise, what we are dealing here with when building with Lego is we are not using, for example, bolts. This is all held together by kinetic friction, static friction. You can bump such a model and it starts coming apart. Plus, we are working with very weak motors, which are again designed to be safe for children, not to perform very well. So our results are quite laughable compared to RC-grade models that you can buy in store. I can tell you, for example, that the current top speed of a Lego vehicle is just under 30 kilometers per hour, and it's quite hard to gather. You are running at the end of what Lego motors are capable of, and when you stop such a model after the top speed test, what you get is a pile of plastic dust because the Lego pieces are grinding. Yeah, some Lego builders are taught to snuff this stuff up, but not that I know of. So yeah, personally, I think that one of my achievements was making a car that weighted 2 kilograms. It's not shown here, but this one was even heavier. It weighted 2 kilograms and it could reach 15 kilometers per hour. That has taken a lot of engineering. And what we see here is that this is an example of a car built with bricks. It has a heavy, blocky appearance, but you can make a lot of details. But there is another way that is closer to the official Lego sets these days. Here we are using typical Technic pieces, which are panels that you can see in the door, which are flexible axles above the front wheel. And this is a somehow simpler way of building that produces a lighter, nicer looking vehicle that has it has less details because, as you can see, some of these pieces are pretty large and you can't really attach anything to them, like the doors. The slot there on the doors, it's a sticker, if you can see. So I was cheating here. And it produces, this is how Lego builds its cars these days, the Porsche, for example, the Porsche set. This is the same technique, and well, I think it looks more sexy than the blocky, heavy fellow here, but you know. And this is a Pagani Huayra model that I have put over a year of work into. It had 10 motors and it had a lot of functions that I'm going to mention in a minute. But when I was done building it, I have compared it to the blueprint of the real thing. And as you can see, it's not perfect, but I think for a model that has 10 motors in it, pneumatics, and a whole ton of other things, I think it's reasonably close. And these are the functions of this model. As you can see, it had rear-wheel drive, 2-speed transmission, doors that could be opened by hand, so nothing fancy here. But the coolest part was the flaps, because if you ever seen the real Pagani Huayra, which is a beautiful car and I strongly recommend that you see it, it's got these flaps that go up and down on the left and right of the body. There is one set in front and another in the back. And what they do is that they increase the downforce on the inner wheels when you're turning. So they increase the downforce on the right wheels when you're turning right and the other way when you're turning left. I think it's a quite ingenious solution, and I wanted to make it happen with a Lego model, and it did, because these flaps, they would move automatically as you were steering this model, and they would also rise, all 4 of them, all sets, front and rear, when you were braking, because this model also had pneumatic brakes on the rear axle. So that's what over a year of building gets you. Here's another example. That's an older model, and it's built with bricks, as you can see. The trick here that it's not very big because it's well, it's medium-sized. It was, I think, about 40 centimeters long. It's built with bricks. It has, as you can see, it has a really smooth appearance. There are no motors sticking out of it, no wires except for that little light there. I didn't want to drill any pieces to, put the wire through. And it looks really smooth. It looks almost like, a static model that does nothing. But if you have an X-ray vision, it actually looks like this. We have three Mindstorms motors, which are pretty huge. We have the entire Mindstorms unit in the back there, and we have some additional sensors and batteries and stuff up there. It's packed up as tight as I could pack it, really. So that's a pretty usual way of doing it on a, let's say high-level hobby building. And you're not going to see this kind of building in Lego sets, unfortunately, because it's really difficult to build this way. Lego is really concerned about its sets being easy to build for kids. If any of you gentlemen remember Lego Technic sets from the 90s, you could get a set that had like 1,000 pieces and the instructions were 30, 40 steps long. These days you have a set that has like 200 pieces and the instructions are 100 pages long and come in several separate books, so the children don't have much difficulty opening these books. So that's where Lego is going, I'm afraid, and that's why the hobby builders, have something to do. Fortunately, that's the most complex model I have ever built. It had 17 motors in it. It had almost 19 meters of electric wiring for the lights, all the motors, all the switches, and it was hell to build because at this level of complexity, I had to. For example, I had to plan to create special tunnels inside just for the wires, to run the wires from the front to the back, because there was no way to just stuff them somewhere. There was so many wires, you had to have special dedicated ducts for them, tunnels or whatever. And it was completely remote controlled. The turn signals were mechanically operated with crankshafts operating electric switches. There was automatic reverse lights, even the first axle in the rear, the second axle technically from the front of the vehicle, it could be raised like in the real track, because in the real track of this type, you can raise the second axle when you are not holding anything heavy, so you can save on the tire wear a little, because you don't need that kind of support. And of course, this is the view of all the motors inside. It's, as you can see, a model like this, making it completely motorized, completely remote controlled is quite complex, because if you just consider the boom on top of there, it has to go up and down, it has to extend forward and backward, then it has to rotate left and right on the base, and then you still have to add winch that pulls the string on and off it. So that's 4 motors just to control the boom. Yeah, so that's a lot of stuff there. And these are all the functions. It even had the lighting, blinking light bar. I have used old Lego bricks from 90s. Again, if any of you gentlemen have played with Lego in your childhood, in 90s there were these nice blinking, very nice, very small light bulbs. Actually, incandescent light bulbs built into Lego bricks. They don't do this anymore. We have LEDs these days, and it's not as cool. It doesn't blink even. So yeah, that was fun to build. I was using some I was using some custom stickers. Yeah, I find it's very rewarding to have the complete model and just think, what stickers am I going to put on it. Here we have a model. How are we looking with time? 10 minutes. Okay, so I'm gonna speed up. Sorry. This is another model I want to show you again. How hard it is to build something like that that's so far from Lego sets, because this is actually my third take on the Lego Hammer, which I like very much. I'm not sure if the gentlemen here are going to like it, but all right. So as you can see here, the red monster here is it's my third take on the Hammer model. You don't get to build models this complex and this good looking. Forgive me for not being modest, but you don't start at this level. You have to get there over the years. And how such a model is built. what we see here, you can see from the size of the Lego minifigure that it's a pretty massive model. I think it was around 60 centimeters long, and it was just driven by 4 Lego motors, 4 strongest Lego motors that they are making. And here we can see the chassis. Again, it's a similar situation as in the Audi model. We have stringers connecting the front and rear axle, and the suspension, that's the interesting thing, because the Hammers have a very rare suspension type. It's a double wishbone independent suspension, but it has portal axles attached to it, meaning that the shafts that come through the suspension, they're actually spinning backwards as you drive forwards, because there are 2 gears inside the wheel hub that increase the gear ratio. Meaning there is a small gear, that the axle that goes through the suspension, it doesn't drive the wheel, it drives the small gear that drives a big gear on the wheel's axle. That's how they increase the performance, that's how you get more torque on the wheels without stressing the structure inside there. Another interesting thing about Hammers is that they have brakes in the middle next to the differential gears, because it's for protection, it's for protecting the brakes, but it's not in my model because it didn't have brakes. It was too slow to need brakes. Yeah. This is an interesting stage because what you can see here is we have front axle on the left, rear axle on the right. There are 4 motors that drive this monstrosity, and there are 2 battery boxes. The battery boxes are actually the heaviest parts of the model. Each of them has 6 AA batteries inside. So as far as Lego goes, this is a pretty heavy piece. And why are they located where they are? You see, because all these 4 motors are putting a lot of weight on the rear axle. So what I wanted to do was to move the battery boxes as far front as I was able to keep the center of gravity close to the middle, because it's an off-road car. You want it to perform nicely off-road, and you don't want to have the center of gravity close to one of the axles. It's going to be unstable, it's going to be likely to tip. So this shows you that even at this early stage, because we haven't even started building the body yet, you have to consider where is most of the weight going to be. It's a lot of planning, as you can see. And this is where we start building the body in a nice red color, as you can see. The funny thing is that the beams inside, the vertical black beams, they are going to brace the body from the inside, because the body is built from the bricks. Again, they are easy to come apart, so you use internal bracing that doesn't show on the outside for such a model to stay together. Here we have a roof and holes for the doors and stuff. Here we have a complete front end and beginnings of the interior. As you can see, even with all this stuff inside, there is still some room for seats and in front and rear. So there can be some basic interior. Here we have more roof and a little more stuff added. Here I kept a hole in the roof when I was working, because this model actually had moving windshield wipers. There was a small motor hanging from the ceiling that was moving the windshield wipers left and right. You could turn it on and off because I had some room to spare, so why not? And what you can see here is another interesting thing, because the Hammer itself is that simple to build. It's a box on wheels, you know. It's not pretty, it's not complicated. But the body, when you consider all the openings for doors and windows, it's actually quite a complex structure with many thin fragments that all have to fit together. It was a lot of calculation to make. The model was like this big. So making it all fit together into one box shape, that was a lot of adjustments. And here you can see the front suspension. As I said, it's a double wishbone suspension with portal axles. You can actually see the gears I've mentioned, small gear driving a bigger gear here. And that increases the torque on the wheels, and it also makes the entire suspension higher, so we have more ground clearance below, enough for this little guy to not get crushed. Yet. This is the bottom view. Like I've mentioned, we have battery boxes close to the front axle. They couldn't be closer because the front wheels, they need some room to turn left and right. There by the rear axle, we have a transmission. It's a simple 2-speed transmission. It's not synchronized. It's operated by sliding gears forward and backwards. This is another example of thinking outside the box, because as you can see, all this lighting, it's custom. It's a single electroluminescent wire. You may be familiar with those. Some car enthusiasts put them everywhere. And the trick is that I wanted this model to be able to drive and have all this lighting on it, which is not really doable if you have to, you know, the wheels have to rotate with wires on them. It gets really complicated. So I have cheated a little because I have put very small black discrete wheels at the bottom of the big wheels, and they were driving. So it was looking from the outside perfectly fine, but the big wheels, they were in fact stationary, and the wires could just stay in place. So depending on what you prefer, it's either cheating or creative thinking. That's an example of my Blackbird model. What you can see here is on the top is a plastic model kit by Revel company, if I recall correctly, and on the bottom is I think it was around 70 centimeters long model made of Lego bricks and with some functions. It had turbines that could spin inside the engines, and it had some illuminated pieces. And yeah, that's a scary hamster on a tank. That's an example of one of my tanks. I have too many of them to show. But this one, it's a K2 Black Panther. It's a South Korean tank, modern one. It's considered by many to be even better than the Abrams tank, more advanced and definitely newer. And the trick here is that the rear tank has completely active suspension. It can sit and tilt on the tracks any way you want it to. And I have wanted to recreate that in Lego models. So what I've done is that I have used torsion bars. So each of the road wheels is connected to an arm that has a bar going through it. And normally you get suspension because this bar can twist up and down. So the arm with the wheel can go up and down. But what I found is that you can attach the other end, the inner end of this bar that goes into the tank. You can attach it to something and turn it. And that changes the angle of the entire arm with the wheel on it. So the entire track, the entire track in the tank can go up and down, and you can make the tank literally sit down. And the trick is that the suspension remains functional at all times, because no matter how far you rotate this torsion bar, it can still flex. It can still, you know, go up and down when there is an obstacle to overcome. And I wanted to finish this overly long talk by admiring perfect German engineering. This is an example of a model that is that simple technically. It drives and steers, it does nothing more. But I believe the original was so pretty that it was really hard to mess it up. So all you had to do to create an impressive model was just to capture a little of this, the beauty of the original car. It's very that simple, but I think it's one of the prettier things I've made. And to sum it up, if you are interested, you can see all this stuff in motion at my YouTube channel, which is called like this. There's no clickbait, I promise, no fidget spinners, no stuff like that. You're not likely to get cancer from watching this. And if you are interested in mechanics in the Lego world, you can try these books, which is accidentally written by me. And it's a lot, because we have barely scratched the surface, I'm afraid. So this goes a lot deeper into that. And it's also available in German. Thank you very much. And if not everyone is asleep yet, I'm happy to take questions, and somebody can play with this monstrosity here, this little thing. And there are my cards on the table if you like.
Thank you, Paul. Thanks a lot.
Thank you very much. Any questions?
How many models do you have, and where do you store them all?
Well, that's the trick, because I don't store my models, I take them apart. I recycle all the pieces I'm using because of how expensive Lego is. So I can tell you that by now I have built a little over 200 models in about 10 years. And I literally have maybe one intact right now. Yes?
So, just without story, I built a Lego Technic model from scratch last Christmas. And it turned out I forgot a piece in the beginning.
Mm-hmm.
And Lego is very anti-modular, I found out. It's very, basically you have to take apart the entire thing
Yeah.
and reassemble it back.
Yeah. Welcome to the hobby.
Well, I did have the booklet telling me how to reassemble it again. But you don't have that. So if you have like a hammer and you build like 100 hours of, you know, chassis and stuff like that.
And there's something wrong inside, yeah, I take it apart.
Is that the wrong way round?
Yeah, you have to take it apart, and, you know,
That's no trick.
there's no trick. No, there's just pain and sweat. Any more questions?
You just mentioned that the bricks are quite expensive.
Yes. Actually, I can tell you it's a quite interesting, great question. Is that the 3D printing, the technology these days is quite interesting in terms of Lego. I can tell you that the Lego itself has an internal working group that's testing how far the 3D printing technology has gone so far. And of course, they are using 3D printing themselves for quick prototyping of new pieces. I've done some tests myself. In my experience, it's still more expensive to print pieces than to buy them, and you still get lower quality. The main advantage is that you can create pieces that Lego doesn't make. You have a total freedom of, I don't know, you can make torsion differentials, which are torque-sensitive differentials, which automatically lock at if the slip occurs. And any kind of piece you want, you're only limited by your own imagination. But in terms of quality and price, the 3D printing is not yet there. I don't know, can you get a micro? All right, I'm going to come closer. It's true that the basic patent for the Lego bricks has expired, I believe, 3 or 4 years ago, maybe more. And as it happened, there has been a rise of rival companies. But we have to differentiate because there are Chinese knockoff companies like Lepin these days, which are basically they're copying Lego sets with lower quality but much lower price. And there are also legitimate companies that make their own original sets that Lego doesn't make. They create their own original pieces that Lego doesn't make. They're only using the same concept that Lego does. They don't copy other stuff. And these include Mega Blocks or Kobe or Playmobil, I believe. Playmobil, yeah. I don't know if they are still on the market, but in my experience, the best of this in terms of quality is Kobe. It's a Polish company, actually. They have won some legal battle against Lego because they got so good at quality that Lego actually tried to sue them to back them off, but they won. And they have very interesting sets, World War II sets, which may interest you if you're into this stuff, because Lego, on the principle, is not making any World War II stuff. In Lego's eyes, it's cool to make a Death Star for children that blows up planets, but a tank is a no-go. Right.
Have you ever tried to build a model where you couldn't make it work, where you had to give up?
I had to give up once so far because I have tried to. I don't know if you know what a bucket wheel excavator looks like. It's one of the largest excavators, one of the largest human-made machines in existence. It excavates at a crazy rate of several trucks per one wheel rotation. But I was overly ambitious. I was trying to make a model that was 2 meters long. Yes, 2 meters long. I had to move some furniture in my house to make it happen. But I have miscalculated the weight that was applied to the chassis. And when I was maybe halfway through, it was 7 kilograms heavy. The chassis started sagging down, and it was impossible to, I would have to start completely over.
You mentioned what society thinks you're doing, and everybody. What does your wife think you're doing?
Here's the trick: I don't yet have one.
Okay, so thank you for it.
Thank you guys very much.